And there are a couple different situations where a B field could be, where the flux could be changing. We talked about moving a magnet closer to it. Now let's say we have a loop, and I'm gonna make my loops in the plane of the page because it's easier to visualize. So we've got a loop, and let's say we have a B field going into the page, and it's generated from some external source, but this source is then turned down. So this B field is decreasing. It's decreasing. It has some strength into the page, but then that strength is decreasing. Okay, so we have flux going into the page, but as the B field decreases, that flux decreases, and the direction it decreases is going into the page. Okay, so as that flux decreases into the page, that means that the flux is, you could think of that as the flux increasing out of the page, but the wire, the loop will generate a B field that opposes this change. So if the B field into the page is decreasing, the flux into the page is decreasing, then the wire will increase the B field into the page, and the B field into the page, put our thumb, curl. So to generate a B field into the page, the current will point clockwise. Okay. Let's say we have a loop, and this is how I'm going to pretend that this loop is oriented left-right. Okay. So, I mean, if we're looking at it straight end on, then it would just be a line, but we're not, so yeah, hopefully that isn't too bad. Let's say we've got a B field going to the left, and that B field is increasing. That means that the flux is also increasing to the left, which the wire wants to oppose. Flux is increasing to the left, so it tries to oppose that change. It wants to generate a B field to the right. In order to generate a B field to the right, the current goes this way, curls around this way. And so that's like this, as I've drawn my little loop. In the side of the loop nearest to us, the current would be going downward. On the side of the loop furthest from us, the current would be going upward. And so hopefully you've got a good idea of how to deal with that. There's another situation where we could have changing flux through a loop, and that's the case where the loop is entering a region of B field. So let's say there's this dividing line, and over here there's a B field going into the page. I'm not going to draw a bunch of circles with X's through them. You get the idea. Over here there is some B field. It's going into the page. On this side of the line, there's nothing. Okay. We've got a loop, and this loop, I don't know if it's being pushed or it's riding a car or whatever, but it has a velocity. It's heading into this B field. So, nothing's going to happen, and then while it's on this boundary line, there is going to be a changing B field, a changing flux. Okay. So that means the flux will be increasing in the direction going into the page, up until the whole loop is inside the B field. The flux is increasing into the page while it's on this boundary line. Since the flux is increasing into the page, the loop will tend to want to generate a field that goes out of the page. And so in order to get a loop out of the page, we put our thumbs up, curl our fingers, and the current would be flowing in this counterclockwise direction. Over here, before it enters the B field, there is no change in flux, so there is no induced current. After it enters the B field, again, there is some flux, but there is no change in flux, and so the induced current, again, is 0. These currents that are generated to oppose the B field are referred to as eddy currents, An eddy is a term that has to do with water. When you move something through the water, there are kind of these spinning vortexes that form as the water flows back into that space that is empty of water. For example, like if you're in a river and there's a large rock, then right behind that rock there's no water directly flowing, in the direction of the river. Say if the river is flowing to the right, and you've got a big old rock here, well, the water is forced to go around the rock, but then, the water is still flowing downriver, and so there is this kind of swirling motion where there's this current that kind of flows back, and then it creates these little circular patterns of water flow, and that's where it gets the name eddy, because it operates a lot like that. These eddy currents also show up when you have a sheet of metal. So if this is a solid sheet of metal, and it's headed downward, and it's leaving some region of B field, this is some region of B field, there are these eddy currents that form. The flux through this sheet is decreasing in the out-of-page direction, and so then there's a current that's generated to counteract that change. So it wants to generate a B field that goes out of the page, and so there's this current that kind of flows around this way. Now, so this eddy current, it generates a force that at the top here, the current's going to the left, and the B field's going out of the page. So at the top here, we point our hand there, curl, it generates an upward force. At the bottom, there is no corresponding downward force because the bottom part is no longer inside the B field. And this is a principle behind what's called magnetic braking, which is used in a lot of things: fishing reels, exercise bikes, roller coasters. It's better than normal braking. In normal braking, you just kind of lay something on the ground and let kinetic friction do its thing. Magnetic braking, the force generated is proportional to the velocity because the velocity affects change in flux, and because it's proportional to the change in velocity, it's more effective at slowing down things that are moving really fast. And also there's no wear on your brakes. Because when your brakes, you drop something on the ground, then that starts to wear away. So with a magnetic brake, nothing is actually rubbing up against anything else, so there's no real wear and tear happening on that.